Hi, good morning, everyone. Welcome back to the webinar. Very pleased to have Ben Wallis from Kishwaukee College, and he's speaking on Garling and Lorentz sequence spaces. Ben?
Thank you. Yeah, so this talk is on Garling and Lorentz sequence spaces. You probably already know what the Lorentz sequence spaces are. Many of you know what the Garling sequence spaces are, but I guess we'll see for those of you who don't. So what makes the study of these spaces so nice is that their canonical bases, their unit vector bases, are very well behaved, especially in the case of the Lorentz sequence space. The Lorentz sequence space basis is symmetric. That means, every permutation is equivalent to the original basis. Subsymmetry is when every subsequence is equivalent to the original basis. Are there any grad students watching? This is kind of for them. So like examples of symmetric basic sequences is like the LP spaces and the canonical basis of the LP spaces and of the C0 space. But there are others. Wallis spaces typically have, well, some of them do have symmetric unit vector bases, as do Lorentz sequence spaces, as we've just seen. So every symmetric basis is subsymmetric, and I guess, so I wasn't around in the 60s, but I guess for some reason people were thinking that the converse was true, but then it turned out that no, it wasn't. Garling published a counterexample in 1968, and he used a variation on the Lorentz sequence spaces, and then these have been generalized. That's why they bear his name now, the Garling sequence spaces. Whoopsie daisy, what was that? I think I just did something weird. Okay. Hopefully this will be okay. Something happened with Zoom. Oh well. If there's any problem, let me know. So let's talk about the definition of the Lorentz sequence space. It's kind of like a weighted LP sequence space. So you've got these weights here, and there is a couple conditions actually on the weights. First of all, you want them normalized, which is to say you want the first element in the sequence to be 1. You want the limit to be 0, and you do not want them to be summable. Oh, and they all have to be positive. So they can't be in L1, they must be in C0, and they have to start with 1. We want to, in fact, I think I forgot to write this down. We want them all to be less than or equal to 1. But we're going to call the set of such sequences like funky W, funky font W, and we're going to always assume throughout this talk that boldface W is in funky font W. The Lorentz sequence space is the space satisfying this norm. This is the supremum over all the permutations of the space, of the natural numbers. You can apply the rearrangement inequality, more on that later, to get the supremum to be attained. And in that case, the norm is given by this, what's called the decreasing rearrangement, or sometimes it's called the non-increasing rearrangement of the moduli of the scalars. And so that's a very nice, this makes it very nice to work with the Lorentz sequence spaces. Not great, but very much nicer than other spaces. The unit vectors do form a weakly null one symmetric basis, and we're going to denote that with the little letters D. And I know this is a little weird. Usually people like XN or something like that. I'm going to go with DN just because it's so darn convenient. And the same with the Garling sequence spaces. The unit vectors of the Garling sequence spaces we're going to denote by little g of n, and that will also be very, very convenient. You can see how similar the definition of the Garling norm is. The Garling norm is basically the exact same thing as the Lorentz sequence space norm. The only difference is instead of taking the supremum over all permutations, well, we take the supremum over all subsequences. That's what this script O represents. Again, the unit vectors form a weakly null basis, but this time it's not symmetric. It's only one subsymmetric, which is still really great, but it changes the geometry of the space quite a bit. And of course, as I mentioned in 1968, Garling proved that in the special case where P is equal to 1 and where the weights W are equal to this n to the negative 1/2 business here, then we get the unit vectors not forming a symmetric basis. They're subsymmetric, but they're not symmetric. And as I said, this was the first known example. We're going to prove later on that this actually holds for all Garling sequence space unit vectors, bases, that is to say, but that'll come later, I suppose. Okay, I do want to mention the weak Lorentz space, and that just consists of this norm here. This is actually not, this is not a Banach space, it's quasi-Banach space. And the reason I mention it is because you can see where the Garling sequence space sits in terms of inclusions. So LP is down here at the bottom. The Lorentz sequence space contains LP. The Garling sequence space contains the Lorentz, and so on. So it goes, right? These are all norm 1 inclusions, by the way. And these are as sets, of course. Okay, so a little background on the Lorentz sequence spaces. So these spaces have been around for a long time, and they were studied before the 70s, but in 1973, and then these three guys, Altshuler, Casazza, and Lin, published a paper, and then in 1974 they published like a sequel paper, and these two papers were just packed with just wonderful, wonderful results. And most of these results that I have listed on this slide are contained in those two papers. So again, these aren't the only two papers, but this was kind of an explosion of results in these two papers on the Lorentz sequence spaces. So I don't know if they're available online. I actually had to go to the library and photocopy like books of these. So I have them if anyone needs them photocopied. But anyway, I digress. So the unit vectors they proved span all of the space, and they form a basis, in fact, a boundedly complete basis, and always weakly null, as is every symmetric basis except for L1. Every basic sequence in the Lorentz space is, which is equivalent to the canonical basis, admits a subsequence spanning a complemented subspace of the Lorentz space. And that gives us, that makes the space complementably homogeneous, which is nice. Not surprisingly, in this third bullet point here, the space is reflexive if P is in the reflexive range, and it's non-reflexive if not, so no great surprise there. No subspace of little LP is isomorphic to the Lorentz sequence space. Lorentz sequence space is not contained in LP. Every normalized block sequence of the canonical basis of the Lorentz space is one dominated by the canonical basis of LP. So this is, and they proved like many more things, but this is kind of some basic overview of what they proved. And so you might ask, okay, so since the Garling sequence spaces are so similar to the Lorentz sequence spaces in definition, how many of these results carry over? And the answer is, of course, all of them. So I won't read this slide to you, but this is basically the same thing with the Garling sequence space. These are identical proofs to the Lorentz case. So nothing surprising here. As I said, the space is complementably homogeneous, as is indeed the Garling sequence spaces, or are the Garling sequence spaces. So what that means is if Y is a subspace, which is isomorphic to the parent space, then you can dip into that subspace, get a further subspace, which is still isomorphic to the parent space, but is complemented in the parent space. So that's true of Garling and Lorentz sequence spaces. So how do you study these spaces? Well, one of probably the biggest tool that I or anyone else seems to use in studying these spaces is this theorem right here. Now, I've given it a name. I just kind of made up this name for the purposes of this talk. This is just something I made up. I need to refer back to this theorem a whole bunch of times, so I wanted to give it a name so I can do that and you guys would recognize it. Anyway, I'll call this the LP subsequence theorem. This holds for the Lorentz sequence space, and it was proved, not surprisingly, in that 1973-1974 pair of papers. There is a version, as it turns out, for the Garling sequence spaces, and here it is. So what we have here is, if you have a block basis, a semi-normalized block basis, such that the coefficients tend to 0, we could call this, we could say that this is uniformly null. That's the lingo that we've been using here. So if you have a uniformly null block basis, then for each epsilon, you can find a subsequence that's that close in equivalence to the canonical basis of LP and that spans a subspace, which is 1 plus epsilon complemented in the Garling sequence space. The proof is very similar, but it's not exactly the same. So it requires passing to something called a minimal, a sequence of minimal vectors is what I really should have said in the slide. So what do I mean by that? What is a minimal vector? Well, so here's the definition of a minimal vector. It's actually probably it's probably best to think backwards, to think of the definition of a non-minimal vector. Suppose you have a vector and you've got all these coefficients. Suppose you take some non-zero coefficients and you zero them out. If the norm doesn't change, then that's not a minimal vector. If the norm does change, well, then might or might not be minimal. But yeah, so if the norm doesn't change, if you can do that, if you can find some coefficients to zero out without changing the norm of that vector, then it's not minimal. And if you can't find any coefficients to zero out that wouldn't change the norm of the vector, then it is minimal. So we're used to, or at least I'm used to, working with like LP and Lorentz spaces where every vector is minimal. If you zero out a non-zero coefficient, you are changing the norm. That is not the case with all the vectors in the Garling sequence space. And indeed, I've given an example down here. This is an example of a vector where you can zero out one of the non-zero coefficients without changing the norm of the vector. This presents not like a huge problem, but it's an annoyance. And it requires, I could imagine it could present huge problems if you're trying to do particular things, but in trying to prove the LP subsequence theorem, you have to pass to vectors that have this property, and then you have to do some finagling to make that work. So it's mostly the same, but there are some differences, I guess is what I'm trying to say here. Okay, so what's an example of something that we can do with the LP subsequence theorem? So the most obvious example is to show that the Garling sequence spaces are uniformly complementably LP saturated. Well, what does that mean? Well, it's kind of like the homogeneity. Well, I'll just read the slide here. It says for every epsilon and for every infinite dimensional closed subspace of the Garling sequence space, you can dip into that subspace, find a further subspace, which is almost isometric to LP and almost one complemented in the parent space, GWP. So that's what that means. In particular, the Garling sequence spaces are all subprojective. How can we use well, it's pretty obvious how to use the LP subsequence theorem to prove this. So you fix an epsilon, you take an infinite dimensional closed subspace Y of the Garling sequence space. Now you can always find by Mazur, you can always find some normalized basic sequence in Y. We want to find a weakly null sequence because we want to use that, we want to pass to like a block sequence, right? So how do you do that? Well, in the case where p equals 1, you can apply Rosenthal's L1 theorem. And then you can ensure that that sequence is weak Cauchy or it's equivalent to L1. If it's equivalent to L1, you have to like apply James L1 distortion theorem. There's something that I didn't write in the slide, but you can get it to work then. If it doesn't, then you get a weak Cauchy sequence. Now that's still not weakly null, but that's no problem because then you can just take the normalized difference sequence that will be weakly null. So that's how you do it in the case p equals 1. In the case where p is greater than 1, well, we don't care because it's reflexive. So every basic sequence is automatically weakly null. So we get this weakly null sequence here. And so by Basaga-Pelczynski, we can pass to some other subsequence to make sure that the y-ends are really, really close to a normalized block basic sequence, which we'll call y prime of the canonical basis. Now, eventually what we want to do is we want to apply that LP subsequence theorem, and we can do that now, right? We can find a block sequence, these z prime n's, which is almost one equivalent to the LP basis, and whose closed linear span is almost one complemented in the parent space. The only trick is you have to kind of like pass between the blocks and the non-blocks, and you do that with this operator T here. And that operator T doesn't change the norm of the complementation or the constant of the complementation. And so you end up with this sequence here, which we'll call Zn. That's applying that operator to the Z primes. And that's your sequence. That's the sequence that spans a complemented, almost one complemented subspace of the Garling sequence space, and which is almost one equivalent to LP. Indeed, almost isometric to LP. And so that's how you prove this particular theorem. Okay, so that's an example of how to use the LP subsequence theorem. And pretty natural, pretty obvious. One of the real nice properties of the Garling sequence space is that it has a unique, up to equivalence, of course, subsymmetric basis. And well, how do you prove that? Well, that's not too hard. Proof's kind of elegant. You assume. So what we're going to, in fact, you can actually do better. Let me catch myself here. It's not just that the Garling sequence space itself has a unique subsymmetric basis. It's that any subspace with a subsymmetric basis, that subsymmetric basis is unique. So in other words, every subspace with a subsymmetric basis has a unique one. So how do you prove that? Well, you take such a subspace. Take Y, which is a subspace with a subsymmetric basis. Now, if it's isomorphic to LP, we're done. So let's assume that it's not. Let's let UNs here, these guys here, let's let those be any other subsymmetric basis for Y. Now, every subsymmetric basis is either L1 equivalent or weakly null. That's not a special property of the Garling sequence spaces. That's just subsymmetric sequences in general. They're either L1 equivalent or they're weakly null. Well, what does that mean? Well, it means in particular that both the UNs and the YNs form weakly null sequences, which, what does that mean? Well, that means we can apply Bosako-Pelczynski, as we always want to do, right? So we get normalized blocks. Okay, so watch what happens here. So the U primes are blocks of the YNs, and they're equivalent to the UNs. The Y primes are going to be blocks of the UNs and equivalent to the YNs. So that's what's going on there. Notice that the LP subsequence theorem says that the coefficients of any subsequence can't tend uniformly to 0 unless they admit an LP subsequence. Well, we decided that that if that happens, we're done anyway, right? So they can't tend uniformly to 0. At this point, you have to apply another property of subsymmetric bases. And there's a very routine argument for this. It's hard to see without writing it on paper, but the basic upshot is that if Yn is a subsymmetric basis and U prime n's are blocks of the Yns that aren't uniformly null, then they dominate the Yns. And so we get this domination here. For the same reason we get this domination here, and putting it all together, we get this string. The Yns squeeze the UNs, and they become equivalent, and that proves the theorem. So, yeah, fairly elegant. Okay, let's see, what else? So as a corollary, the unit vector basis Gn is the unique subsymmetric basis for the Garling sequence space. By the way, I should mention that this is also true for the Lorentz sequence spaces. The Lorentz sequence spaces have a unique symmetric basis and subsymmetric, but who cares, up to equivalence. All right, so those are some of the basic properties of the geometry of the Garling sequence spaces, and to a lesser extent, the Lorentz sequence spaces. Let's talk about how we know that the Garling basis is not symmetric. It's subsymmetric, but it's not symmetric. And the reason has to do with this theorem right here. So this theorem was published in a paper called Optimality of the Rearrangement Inequality. I think this is out of all the slides, I think this is my very favorite thing that I'm giving to you guys. This is my favorite theorem from this whole presentation. The reason I like it so much is because it's just an analysis inequality. It strikes me, I might be wrong about this. I don't know, maybe I'm wrong. It strikes me that that this could, I'm hoping that this is useful for other things than just like Banach space theory and stuff like that. But it's basically what it says is that if you take, two sequences, BIs and AIs, and you get the worst rearrangement possible, then you can still ensure that this inequality holds, provided that the second condition holds. Either the BIs are not they don't sum to infinity, or their infimum is not 0. So, and these are actually equivalent. But provided you have this condition here, you can rearrange as much as you like, and this inequality will still hold. So this looks to me to be a really cool theorem, and it's useful in particular for proving that the Garling sequence space basis is not symmetric, and in particular because all the subsymmetric bases are equivalent, that means that the Garling sequence space does not admit any symmetric basis. So how do we prove it? I don't know if I want to go through this slide in detail. It's kind of technical, but the basic idea is you assume towards a contradiction that the basis is symmetric. You let the wi's, these are the weights, remember, these are the weights of the Garling sequence space. You let those play the role of the bi's in the optimality of the rearrangement inequality theorem. And then you apply the Garling norm here. This is just kind of a supremum. Well, it's not kind of, it is a supremum over the subsequences. You have to do a little bit of finagling here, and there's a way to do that by making sure that all these inequalities hold, making sure that the AIs are non-increasing, which you can't assume with that loss of generality. But eventually, you get the very inequality that was given in this previous slide here. You get this inequality right here, and you get it for an arbitrary sequence of non-negative scalars. Well, that means that it's equivalent to 2, remember. That means that, one of these things must hold. But by definition, neither of them do, right? By definition, W is not in L1, and I forgot to write it down here, but it is in C0. And so that's a contradiction with the optimality of the rearrangement inequality. And so that's the sketch of this proof here. So yeah, so again, I'm hoping that theorem is useful for other things than just this. It was created for this, but hopefully it has more uses than that. Okay. As a corollary, no subspace of the Lorentz sequence space is isomorphic to the Garling sequence space. How would we prove it? Well, suppose otherwise, towards a contradiction. Then you can find a basic sequence in the Lorentz space, which is equivalent to the Garling basis. Now, this basic sequence, because it's equivalent to the Garling basis, would have to be subsymmetric. So therefore, it's obviously not equivalent to L1, so it has to be weakly null. So we can apply the Saga-Pelczynski. That gives us a block sequence Y prime, which is equivalent to the original YNs. And that's a block sequence of the DNs, I should mention. And then we have to apply one of those 1973, 1974 theorems from the Altshuler-Casazza-Lin papers. It says every subsymmetric basic sequence in the Lorentz sequence space dominates the canonical basis. Well, what does that mean? Well, we know then that the Y prime ends dominate the DNs. That's what we just said. These are equivalent to those. Those are equivalent to those. And it should be obvious from the definition that the Garling basis is one dominated by the Lorentz basis. And so this is squeezed together to make sure that the GNs are equivalent to the DNs. Well, that's a contradiction because the DNs, those are the Lorentz, that's the Lorentz basis. That's symmetric. The GNs are not symmetric. So it follows then that no subspace of the Lorentz space is isomorphic to the Garling space.
Didn't you just prove that every symmetric basic sequence is LP?
Every symmetric basic sequence is what?
Is actually LP in this Garling space.
Well, not the basis itself, right? And
no, what I mean is there are no symmetric basic sequences in the space other than the LP.
No, we don't know that.
I think we just proved that. Your proof just changed the Lorentz thing to. So there's a little bit of So
let me give you an example. So in the Lorentz sequence space, you can, depending on the weights, you can make it so that there are exactly 2 basic sequences in the Lorentz space, or like infinitely many. I think it's infinitely more than 2 at any rate. So that couldn't be, right? Because if Well, if the Garling sequence space is anything like that, then it couldn't be, right? Maybe I misunderstood.
What I want to say is that in Garling sequence space, it seems to me that if a basic sequence is symmetric, that already implies that it has to be level LP. So there are no non-trivial symmetric sequences in Garling.
Oh, symmetric.
Yeah.
That's in another paper.
Is it?
Yeah, well, that's with Albiac and Surena and Dilworth.
Okay, yeah, I mean, it should follow, or because that it contains L infinity ends, right? So the symmetric basic sequence cannot contain that. That might be another way of looking. This is very similar to the Freire spaces.
Could you do it like this? How long was the proof in the other paper? Was it like this short, like this?
It was not short.
Okay.
the domination thing is missing here. So in the Lorentz sequence spaces, you said that every block sequence is dominated by. So that part is missing. So you have to do something about it, probably.
Well, but that's proved in the Casaza-Lin paper.
I mean, for arbitrary symmetric sequence.
Oh.
No, I mean that doesn't hold for arbitrary symmetric sequences.
Yeah, I don't know.
Okay, sorry, go ahead.
No, that's fine. I need some filler. Okay, so let's see here. But yeah, so that's basically all I wanted to say about the sequence structure. But there's also some applications to ideals that I wanted to look at because I was into that for a while. I guess like in the last 20 years, I think it was like 2002 was the first paper to like kind of rekindle interest in, studying the closed ideal structure of these operator algebras. And in particular, in 2012, these 5 fine folks published this really awesome paper. It's the first detailed study of the lattice of closed ideals for the Lorentz sequence basis. In fact, as far as I know, it's the only detailed study. And they proved a whole bunch of things, but among what they did prove is this diagram right here. So you can take a moment to read the diagram. I'm not going to read it to you. It's pretty self-explanatory. All the notation is pretty standard, and the notation that's not standard I have down here. This JD, this is the formal identity from LP into the Lorentz space. The J, that means like JLP, those are the LP factorable operators. And this looks more complicated than it is. The truth is, even though there are a bunch of like ideals listed here, we really only, at least up until this research here, we really only knew that 5 of them were distinct. So depending, because a lot of these subset relations, they're just subset relations. We don't know if they're actually distinct here. Some of them are. And one of the really nice things about what they did here in this paper is they found not only that they're distinct, but they found some unique immediate successors, which is really cool. But yeah, so that's what they proved. And so if you're going to look at the Garling ideal structure, as of course I wanted to do, the very first thing is to check and to see how much of this holds up. And well, pretty much all of it carries over. In fact, the only thing that doesn't carry over, the only reason that I don't know it doesn't carry over is because I simply didn't have time to check. I've just been so busy. I didn't check that the finitely strictly singulars are the same as the regular strictly singulars. They probably are, but I simply haven't had time. But all the other stuff checks out. So we kind of have a leg up here. Like we have a head start in studying the closed ideal structure of the Garling sequence spaces. So what can we do? How can we further explore this closed ideal structure? Well, I'm sure Thomas is going to laugh here because in 2015, Thomas Schlumpfrecht and Andrzej published this paper on the bounded linear operators of LP plus LQ, and showed that they contained infinitely many ideals. In fact, a chain, cardinality, the continuum, many closed ideals. And their main tool was to use these like projections, string together these projections onto these finite dimensional versions of the Rosenthal XP spaces. And so, you know, I like this. I was a grad student when I was reading this paper, and so I noticed that they didn't need as strong of assumptions as they used, and so I was like, well, you can do this with it, right? And so I got a paper on that, and I did other things, obviously, but then I was looking at it again. I was like, I'll be darned, you really don't need much, and you were able to really weaken the hypothesis even more. And so this is as you probably weaken them still further, but this is as weak as I got them. Here's what we need. We're going to take a P, and P has to be between 1 and 2, and you have to have a complemented copy of LP. Now that's restrictive. Make no mistake. That's horrible. But a lot of spaces do have that. A lot of spaces do have a complemented copy of LP with P between 1 and 2. In particular, obviously, the Lorentz spaces and the Garling sequence spaces. Okay, what else do you need? Well, you can take a Q that's greater than P. That's the only restriction on Q. All it has to be is greater than P. Otherwise, it can range however you want. And then you get this space here, which is the LQ sum of finite dimensional copies of L2. Now, you don't need a copy of the space. Nothing so restrictive as that. All you need is a normalized or even semi-normalized basic sequence in your space that's dominated by this space's basis. It doesn't have to be equivalent or anything. It just has to be dominated. That's all. Now, I could be wrong. Maybe I'm wrong. But that doesn't seem very restrictive to me. It seems like there would be lots of spaces that could have a basic sequence dominated by this basis. And so yeah, so that's what I tried. Oh, and by the way, this is only for real Banach spaces, but it does hold if you take the complexification as well, so you get the same result. Please also note that you can always take Q to be the number 2. And if you take Q to be the number 2, well, this basis is just the L2 basis. So for instance, anything dominated by L2 will work. And that's exactly what I did. And this is so cheap. I know I'm fully aware how cheap this is, but I wanted to do it anyway just to see if I could get it to work, and it does. So you restrict P to between 1 and 2. And what I did is to get my a basic sequence that's dominated by L2, all I did was I took a weight to be in this little L space, right? And if you take this, if you take the weight to be in this little L space, well, these two numbers are conjugates, and then you can use Holder's inequality to get the canonical basis bounded or dominated, if you like, by L2. And yeah, I know it's a cheap thing to do, but I don't know, like, why not? So I did it. And so it follows then that how do you say, the Lorentz basis is dominated by L2. So by the way, is the Garling basis. Same thing works for the Garling basis. Obviously, LP is already complemented. And so for these particular special cases of both the Lorentz and the Garling sequence spaces, you get a chain of closed ideals with cardinality of the continuum, which are all, and they're, by the way, they're also all LP factorable, and they're all finitely strictly singular. So yeah, so thank you, Thomas Schlamprecht and Andrzej Zak. It's the theorem that keeps on giving. All right, so yeah, so what does this tell us? Well, only for this special case, obviously, or these special cases, but boy, it's I don't know, to me, it's strongly suggestive that we'll probably get, it's probably going to hold, something like this is probably going to hold for all cases, is what I'm guessing. I don't know for sure. I guess the big question is, can we do the same thing with the, so people have been publishing these where they prove that the cardinality is like 2 to the 2 to the C of closed ideals, which I guess is like the biggest that you can have for a reflexive, for a separable space. I wonder if you could do that here. Again, I just haven't had time. Probably, I would think. Okay. So yeah, so there's that. What else can we say? Because those were just special cases. Can we get anything in the general case? Well, yes, we can. At least in the Lorentz case. Not necessarily in the Garling case, but probably. But definitely in the Lorentz case. And how are we going to do it? Well, first thing that I looked at was this Altshuler theorem from 1975. So this isn't that pair of papers, but it like came right after. He basically proved one thing in that paper, one main thing, which is this theorem right here. If you look in the reflexive range, you can get the space failing to be super reflexive if and only if the weight W satisfies this NUC condition, which is right here. Obviously, if it's not in the reflexive range, then all bets are off. The way he did it was to find finite dimensional like copies, like really nice finite dimensional copies of L infinity. And so I got to thinking, well, could we string together those finite dimensional copies of L infinity to maybe make an LP sum of L infinities? Then maybe it could be complemented. And so, yeah, that's exactly what happened. So, so I'm going to use this notation here, WP comma infinity, to refer to this LP sum of finite dimensional copies of L infinity. And it turns out that, yeah, so if the weight W satisfies that NUC condition, then the Lorentz sequence space admits, and by the way, so does the Garling sequence space, but they admit complemented copies of that WP infinity space. Now, I don't think it was like a month or two before Denka and company kind of one-upped me here. That's okay, that's great. They proved that, in fact, this holds, they didn't use, oh, let me rewind a bit here. To do this, I used very, very standard thing, very easy thing, which is to take constant coefficient blocks of the canonical basis. Any constant coefficient blocks are automatically one complemented if you have a symmetric basis, and they're automatically two complemented if you have a subsymmetric basis. It's a very natural thing to do if you're looking for a complemented subspace. But Albiak and Serena, Dilworth and Kutsarova all proved in 2020, it was finally published, that every Garling sequence space admits a complemented copy of WP infinity. Now, they didn't use constant coefficient blocks. They used blocks of constant coefficient blocks. And that's something that you can't do in the Lorentz case. It only works for the Garling case. So that's awesome. So we have a non-trivial complemented subspace of the Garling sequence space. To my knowledge, this is only the second non-trivial complemented subspace of the Garling sequence space after, of course, LP itself, right? LP and the space itself, I should say, but the space itself would be trivial. So how are we going to do it for the general case, though? Because this doesn't work for the Lorentz sequence spaces. My idea was to use finite dimensional copies of the Lorentz sequence space itself. So that's what I'm going to do. I'm going to use this notation here. We're going to define the dn's to be the linear span, or the closed linear span, if you like, of these finite dimensional stretches of the canonical basis. And then I'm going to take the LP sum of those. I'm going to call this this space YWP. Excuse me. Now I want to prove that once I prove that this is complemented in the Lorentz sequence space, which I will do, I wanted to prove that it is in fact a non-trivial complemented subspace. That is to say, it's not isomorphic to the parent space. It's not isomorphic to the Lorentz sequence space itself. And also that it's not isomorphic to LP. Proving that it's not isomorphic to the Lorentz sequence space is no big deal. Proving that it's not isomorphic to LP is more complicated, but thank goodness for William B. Johnson, because he basically held my hand through this proof here, which is that if we look in the reflexive range, it doesn't work for p equals 1, but if you look in the reflexive range, you can like do an ultra power proof to prove that no LP space, including little LP, but no LP space at all, contains uniformly complemented copies of those finite dimensional Lorentz sequence spaces. And so that was the missing ingredient. And so thank you to William B. Johnson for filling that in. Once you have that, everything falls out nicely. So this space fails to be isomorphic to LP. Obviously, it's, well, not obviously, but I'll show later that it's not isomorphic to the Lorentz sequence space itself. And what I did was in my preprint here, I proved that under this specific condition here on the weights, and don't worry, I have a general case to take care of the non-specific condition, but under the specific condition, the Lorentz sequence space contains a complemented copy of this YWP space, which is spanned by the constant coefficient blocks of the original basis. Now, I do have something for the general case, as I said, but before I do that, I wanted to mention this case, and make no mistake, it's restrictive, but it's not quite as restrictive as you might think. Casaza and Lin, in the 1974 paper, obviously, proved that any weight satisfying this condition here gives rise to an isomorphic Lorentz sequence space satisfying this condition that I used. So, I mean, it's still restrictive, but not quite perhaps as restrictive as, you know, having these actual weights. Okay. So that's great. Again, I mean, that I was pleased. But what about the general case? Because that's really, I mean, that's what we all want. We all want something that you can just not worry about it, regardless of weight, regardless of P. How are we going to do it? Well, we need some notation. So for each natural number K, I'm going to use this like superscript parenthesis K here notation to denote the basic sequence formed by taking normalized constant coefficient blocks of length K. And this is actually one equivalent to a different Lorentz basis, where we have these different weights. And these weights are just the weights that are generated by these constant coefficient blocks. And so these weights here form, they're still normalized. They still go to, they still are in C0 and they still are not in L1. So they do form a standard Lorentz sequence space. Note that these sequences are equivalent, but they're not one equivalent. But again, this is one equivalent to this space's basis. And so that's how you get this theorem here. This theorem says that there is an increasing sequence of integers such that if you take these constant coefficient blocks and you grow them sufficiently fast, they will span a one complemented subspace, which now it's not isomorphic to this where was that space? There. It's not oops, sorry. It's not this space here exactly, but it behaves very similarly. And in particular, it contains no isomorph of the Lorentz sequence space itself, and it's not isomorphic to LP for much the same reason that the other space wasn't. And so this gives us, in the general case, regardless of P, regardless of weight, an infinite dimensional complemented subspace, which is isomorphic neither to LP nor to the Lorentz sequence space itself. And again, as far as I know, in the general case, this is only the second non-trivial subspace known of the Lorentz sequence spaces. Okay, let's see, how many slides do I, should I go through this proof? How many slides? Yeah, I don't think I'm going to go through this proof. I don't think we have time. But basically, yeah, it's well, you can, I think it's being recorded. If you want to go back and pause the recording or just look at the paper, you can see. Okay, so we have a non-trivial complemented subspace, another one. Can we use it to generate a closed ideal? Because that's, I don't know, it seems to be what I always do. So, and the answer is yeah, you can do that. At least in the Lorentz case. I haven't had time to try it in the Garling case yet. Probably worse for the Garling case. You need two ingredients though. You need these two ingredients here. These two ingredients basically say that you can get, what I'm going to do is I'm going to apply LP to play the role of big Z there. So the LP factorable operators are going to be a proper ideal in both the Lorentz sequence space operator algebra and the Y space operator algebra. And also any projection onto LP generates the LP factorable operators. That's the other thing that we get, again, provided that you have those assumptions. And then I also needed a result from this Louston Loy Reed paper back in 2004 when all this stuff started to be kind of rekindled. And this says that under certain conditions, in particular, if you have LP, the strictly singular operators are going to be contained in the LP factorable operators. Again, under these conditions. Okay, so with those two preliminaries in hand, you can prove this. You can say, let Y be the complemented subspace of the Lorentz. That's the non-trivial subspace that we just found, right? Take any projection with image of Y, and that projection is going to be a member of this set. Now, what does this mean? This set here, this is the ideal of Lorentz space singular operators. That means any operator that is not bounded below on an isomorphic copy of the Lorentz sequence space. This is actually the maximal ideal in the space. So the projection is going to be in that maximal ideal, which is not surprising since it is the maximal ideal, but it's not in the join of the LP factorable operators with the strictly singular operators. And so once you find such an operator, it follows immediately that that join is a distinct ideal from the Lorentz singular operators. And do I have time to prove this? Probably not. I think I've only got 4 minutes, right? I do want to show one part of the proof. The mechanics of this proof is to make this note right here. To note that the join of two closures, two closed ideals, is equal to the closure of their sum. And since the LP factorable operators are an ideal, not just like a set, they're an actual ideal. All you need to do is you need to assume towards a contradiction that this projection can be approximated by some LP factorization plus a strictly singular operator. You compose a projection together with its embedding counterpart on the left and right, and this gives you an approximation of the identity operator on Y with an LP factorable operator, which is, I guess, this guy here, right? And another strictly singular operator, which is this guy here. And this shows that the identity operator on Y is in the join of the LP factorable operators and the strictly singular operators. And that generates a contradiction because the strictly singular operators are contained in the LP factorable operators. And so their join is just the LP factorable operators. Well, the LP factorable operators are proper ideal by that Loy-Lawson theorem and Reed theorem. Well, that means that the identity operator is not in the join, which is a contradiction. And so it follows that the projection is in the join as desired. So that was a very quick sketch of the proof. I apologize for running out of time there, not being able to take it in more detail, but that's the basic idea of the proof. So yeah, so we get a sixth distinct ideal on top of the 5 that we knew in the general case for the Lorentz sequence spaces. I haven't had a chance to check the Garling case, but probably holds, but maybe not, I'm not sure. That would be something that I'd have to sit down and do. Before I close up shop here, a few conjectures. So these 3 conjectures are, I don't know, they strike me as being difficult to prove, but I wanted to give an example here because if these 3 conjectures could be proved, if you remember that big kind of sprawling outline of the lattice of closed ideals for the Lorentz sequence spaces, if you could prove these 3 conjectures, that whole thing would collapse into this nice little chain here. And look at all these unique immediate successors. The only remaining ideals would fall right in here if these 3 conjectures were true. So I don't know, that seems like something to investigate, but it seems difficult. So yeah, so I'll need more time before I can do anything like that. But that's something to think about. The other things that to think about are, does every constant coefficient block basis in the Lorentz sequence space span a subspace isomorphic to one of those 3 spaces? We know the Lorentz space itself, obviously. We know LP, and we know the space Y that we constructed. Are there any other spaces? I suspect not, but I don't know. Again, time is an issue. So, well, not just time, really. I mean, these are difficult problems. And so finally, is the analogous complemented subspace Y in the Garling sequence space isomorphic to LP? I haven't actually proved that. So that would be worth looking at. But those are some questions and conjectures, and I think that's about it. And yeah, I think I'm right on time for ending. So that is all. Thank you very much.
Thank you, Ben. Questions or comments?
Yeah, Ben, would you go back to proposition 2?
Sure. This one? This condition, by the way, they call this semi-spreading.
Oh, okay, right, yeah.
Yeah, and it's actually a much larger theorem, but I kind of trimmed it down to what I needed.
Yeah. Okay, yeah, I remember now. So you don't know that there may be infinitely many complemented subspaces of these Lorentz spaces, right?
Yeah, I mean, it's hard to say, but when I see infinitely many closed ideals, I tend to think probably infinitely many complemented subspaces too. That's the way my intuition runs. But I don't know. Nobody knows as far as I know.
And you don't know that they all have unconditional bases or anything, I guess. I'm sure that's still open, right?
If what has unconditional basis?
A complemented subspace of a Lorentz space.
Oh,
That's.
I actually that never. I have no idea. Yeah, that never occurred to me to check.
I would assume that's still open.
Yeah, well, that's an interesting. Yeah, that would be interesting to check. I don't know. Yeah, I mean, there's a lot of open stuff here, for sure. I think I almost have a question about what was the theorem that you mentioned that the Denko or excuse me, it was the Dilworth paper. What was this now? I don't think I've seen this.
Well, actually, when you said that you were citing one of our papers, I thought originally that you might be citing exactly that one. But in fact, this is a different one when we had that you can have continuum many non-equivalent subsymmetric sequences, but the symmetric basic sequences are just equivalent to LP.
Oh, right. Yeah. I think I did see that paper, but I must have forgotten about it. I think I did see it briefly.
Yeah, actually, since, as I said, I'm not very good at finding things on archive or computers, and now we don't go even to the library. You offered to send even the Altschuler, Kazaza, and Lin papers and so on. And since we don't go even to the department, plus some of these, the papers which you had with that inequality and so on, would you send them to me? I would be
certainly send them
thankful.
Yeah, yeah.
And then maybe sometimes we can even talk on Zoom or something, but now you can't visit, even if you're close. I mean, it's... Yeah.
Well, yeah, no, definitely. Actually, I don't mind Zoom. I've kind of secretly been enjoying this.
Yes, me too.
Well, okay, put it that way. I do enjoy that I don't have to go to the department and teach when many students are coughing, not from the new virus, but in general.
Yeah.
That I have to say it's a relief, but I do miss seeing the colleagues. If I want to talk math with Marius Junge, well, I can't stop him in the coffee room and he doesn't reply to emails. So how do you deal with that?
I'm sorry. Yeah.
So
no, it's okay. It's okay.
Ben, I have a question still.
Sure.
Hi. Very nice talk. I enjoyed it very much. So
Yeah,
you said, if I remember well, you said that you know that there are continuum many closed ideals in the Garling space.
Yeah.
But you don't know two to the continuum.
No.
So have you looked at the paper? I mean, have you looked at the paper Dan and Androsh recently wrote, and it's on the archive?
Yeah,
I have. Like a general content, and in some sense, together with this, together with Bill's and Giddon's idea, it's almost unavoidable in some sense. Yeah. Actually, it would be more interesting to have only continuum many closed ideals. This would be nowadays.
Well, that sounds like who's Lawson and Tomek Kania, they could probably cook up something like that.
Yeah. So
they
you might. So okay, you looked at it, and the same arguments don't. So the arguments we had in the paper with Dan and Anders don't work, or
Well, no, I again, like, so I've just been busy. I haven't had time.
yeah. Okay. No,
Yeah,
but it
no,
might.
I suspect they do, to be honest. That's what I was saying, that I think they probably would, but I haven't had time to check.
Yeah, by the way, actually, one of the only spaces we cannot apply our method is C0 plus little l1, where you guys still have the best possible.
Oh, really?
You still have with omega 1, you still have the
the Searleson thing, yeah. That was fun.
yeah, exactly. There you still have the
I'm
the
sure
best
it
possible
has
result.
to, though. I mean, obviously that won't work, but I can't imagine that they all do except that one. I just can't imagine that.
Well, because it comes from there are fewer complemented subspaces, right? C0 and little l1. So
maybe, I don't know.
there's a good reason for it not to work. Okay.
Maybe, yeah. Be a surprise.
So this complemented subspace you call Y, this was the LP sum of the initial pieces, right?
No, actually, that's the thing. I should have mentioned that, actually. That is an open question. It seems like it should be an LP sum of like something, right? So this, where is it? Yeah, this thing here. This is definitely an LP sum, no question. But that's only in that special case where the weights are like this, right? In the general case, the construction is the same, and the proof that it's non-trivial is largely the same. But
what was the definition of Y again? Sorry.
Well, I don't think do I have it here? Okay, here's the definition of Y. So you take these constant coefficients blocks, okay, and you find a long length for each block. Take a long string of these same length blocks, right? They're going to be equivalent to well, they are the finite dimensional version of the Lorentz sequence space, right?
Right.
And they're complemented in Y because they're just part of the basis for Y. But just because they're complemented doesn't mean they form an LP sum like that. And I'm thinking they probably do. And I did try my hand at it. I tried like seeing if I could get all the inequalities to work out. I couldn't do it. And so I kind of just shrugged my shoulders and I said, okay, so, I guess I'm not going to do that. But yeah, I mean, it seems like it should be an LP sum, but I can see no proof of it.
I mean, if you vary the dimensions, like, do you know that you're not getting different spaces at least?
What do you mean?
Maybe I'm still not understanding the definition. So these are like finite dimensional pieces pasted together, correct?
Yeah, they're finite dimensional. Okay, so yes and no. They're not spaces being glued together. They're finite sequences being glued together.
Right.
Okay, and each of those sequences spans a finite dimensional space. But the gluing isn't by spaces. The gluing is by sequence. And so there's not really any glue at all, really. You're just taking a constant coefficient block sequence where the length of those blocks grows. That's all you're doing. It's it's kind of cheap, to be honest, but you can prove that they form like little LP little blocks glued together by an LP norm when the weight is nice. But when the weight is some arbitrary thing that you don't know, at least for my own part, I wasn't able to do that.
Thank you. Any other?
And I did try. I did try that. But I don't know.
Okay, thank you so much again. Very nice talk. Appreciate it.